So hello everyone, today we're going to be doing another integral problem, namely the integral of dx over sine x times 2 plus cosine x. Okay, of course we could do this by using the universal trig sub that I've made a video about yesterday, but I want to try a slightly different approach with this problem here. Okay, so we're going to use another kind of sub, namely 2 plus cosine x is equal to t, and therefore minus sine x dx is equal to dt, or in other words, dx is equal to dt over negative sine x. Now, what I'm about to do now is a little bit out of the ordinary, but you'll understand what I'm doing in a second. So here I'm going to just write 1, and instead of dx, I'm going to put dt over minus sine x, and here I'm also going to put in sine x, and instead of 2 plus cosine x, I'm just going to put in t. Now, why did I do this? Because now I have the integral of dt over the negative integral of dt over sine squared x times t. Now, what can I write sine squared x as in terms of t? Well, from this substitution right here, we get that cosine x is equal to t minus 2. So cosine x is equal to t minus 2. Okay? Well, I'm just going to write it here. Okay, I'm just going to rewrite that somewhere here as 2 plus cosine x is equal to t. Therefore, cosine x is equal to t minus 2, or in other words, cosine squared x is equal to t minus 2 squared. Now, cosine squared x can be rewritten as 1 minus sine squared of x, which is still the same as t minus 2 squared, or in other words, sine squared x is equal to 1 minus t minus 2 squared. Okay, t minus 2 quantity squared. Now, with this in mind, I'm just going to go ahead and plug this in back into our integral. So we're going to get the integral of dt over, since we have this minus here, I'll just change the signs of these two, okay, of t minus 2 squared minus 1 and of course times t. Okay, now of course we can rewrite this. We see here a difference of two squares, so we can rewrite this integral as dt over t minus 2 minus 1 t minus 2 minus 1 times t minus 2 plus 1 times t. Or in other words, we get the integral of dt over t minus 3 times t minus 1 and times t. Okay, now we can rewrite this here part. We can separate this integral into several less complicated integrals. Namely, what I'm going to do is I want to do partial fractions on this quantity right here. T minus 3 times t minus 1 times t is equal to a over t plus b over t minus 1 plus c over t minus 3. Okay, now what I'm going to do now is use the cover-up method, the so-called cover-up method, to find these unknown coefficients a, b, and c. So what we want to do in order to find the coefficient a, in this case, is to ask ourselves first, what value does t have to have in order, what value does the denominator have to have in order for it, okay, let me rephrase that. What value does the t in the denominator have to have such that the entire denominator is equal to 0? In this case, it's easy. T is equal to 0. Then we're going to cover up this here part. We're just going to pretend like it doesn't exist, and we're going to put in that value into the rest of our equation. So therefore, a is going to be equal 1 over 0 minus 3 times 0 minus 1, so which is minus 3 times minus 1, which is 3, so a is equal to 1/3. Now we're going to do pretty much the same thing with the other two. Now, what value does t have to have here in order for this denominator to be 0? It has to be, t has to be equal to 1. Okay, so now we're going to cover up this part right here, and we will plug in 1 into the rest of this here part. So b is equal to 1 over 1 minus 3 times 1. Okay, which is equal to 1 minus 3 is negative 2, so it's equal to negative 1 over 2. Okay, and what do we have now? All that we have that's left is to find the value of c. Okay, so t minus 1 is right here, is to find the value of c. So again, in this case, t has to be 3, and we cover this part up, and c is equal to 1 over 3 minus 1 times 3, which is equal to 1 over 6. So Now, and you can only use this cover-up method if you don't have any solutions that are multiple. Okay, so if we were to have a square right here, yeah, this wouldn't or here for that matter, that wouldn't work, this wouldn't work, and you would have to make a system of equations and go the long way. Or if you have any complex solutions, or if you have any squares, anything to the square, anything to the cubed, anything that's not factorable, this cover-up method won't work. But in this case, it works beautifully. Well, okay. So this here now means that we can rewrite our integral of dt over t minus 3 times t minus 1 times t as the integral what do I have first? A of 1 as 1/3 of the integral of dt over t minus 1/2 of the integral of 1 over t minus 1, I mean dt over t minus 1, plus 1/6 of an integral of dt over t minus 3, which is simply equal to 1/3 ln t minus 1/2 of ln of t minus 1 plus 1/6 of the natural log of t minus 3. And don't forget to add a plus c, plus some constant. So what we have here now is we've solved our integral, but we have to bring it back to the to the x world. And we said that t is equal to what? 2 plus cosine x. 2 plus cosine x. So 1/3 of ln of 2 plus cosine x. And yeah, we don't need the absolute parentheses anymore because 2 plus cosine x must be a positive value. Why? Because the minimum value that the cosine of x can have in the real world is -1. And in that case, we would just get ln of 1, which is 0, but it is still defined. Minus 1/2 of the natural log of 1 plus cosine x. And in this case, we can get that, yeah, we can possibly get ln of 0, which isn't defined. And finally, plus 1/6 of ln of 2 minus 3 of cosine x minus 1 of cosine x minus 1. So we will have to have still the absolute value in this one. Why? Because this expression right here can either be negative or 0. So plus c. So our final answer to our integral, to our problem, is that the integral of dx over sine x times 2 plus cosine x is equal to 1/3 of ln of 2 plus cosine x minus 1/2 of the ln of 1 plus cosine x plus 1/6 of ln of cosine x minus 1 plus c. So that's our answer to this problem. Thanks for watching, and if you enjoyed the video, make sure to subscribe and hit that thumbs up button. I'll see you in the next one. Goodbye.